Hello. We're all pretty aware that I-beams are very strong, but I wanted to evaluate what would happen if we decided to build our buildings with RIT beams. So we're going to take a look at the relative strength of an I-beam relative to an R-beam and a T-beam in this video. Here we can see our end goal, where eventually we'll show that a 5-foot long R-beam with 300 pounds of force will deflect about 2/1000 of an inch, where an I-beam will deflect 1/1000 of an inch and the T-beam will deflect 1.3 thousandths of an inch. So this is where we'll get to by the end of this video. And I'm sure you have a lot of questions and hopefully those will get covered throughout the video. So I've started here with a step one, right? We're going to create the beams. I'm going for a 6-inch tall beam that's 5 feet long. And this support is going to be necessary when we get to those simulations. My first sketch is my RIT with the Tenos font, which kind of replicates that Times New Roman font. I've given it the 6-inch height. However, you can see here that 6 inches does not apply to the actual size of the font. We're going to go ahead and leave it the way it is, acknowledging that we want 6 inches, but what we're getting here is not 6 inches. We're getting 5.45. So this one we're going to go ahead and add as a variable. We'll call it H1. Okay. And we're going to measure between those two faces. And it's going to save this H1 here as the height of that beam. So step one, create the beams. Step two is going to be to scale the beams to reflect the desired height. So we know what we got. We're going to create a new beam that's 6 inches tall by going into our transform. We're going to select R and I and T. We are going to scale those, not uniformly. I want to leave the Y depth the same. I don't want to leave the Y scale as 1. So X scale is going to be 6 over H1. And the Z scale is, it's got to be 6 inches because H1 is in inches. And 6 inches over H1. So we're going to have about a 1.1 scale. Okay. And let's scale it around the origin. Okay. We can see everything gets a little bit bigger. Okay. And don't worry about this. This is all going to kind of work out in the end. You'll see. And so just to confirm, if I go from the top of the T to the bottom of the T, we are exactly 6 inches. Okay. Perfect. Okay. Step two, scale the beams. Actually, so transform was step two, where we scaled the beams when we got to the desired height. Step three, we're going to find the centroid of each face and compare the weights of the beams. So all of these beams already have a mass assigned to them, or a material assigned to them. We can see that the mass of the R beam is about 75 pounds. The mass of the I beam is about 35 pounds, about half the mass of the R. And the T is higher than I, less than R at 48.5 pounds. But those all have aluminum assigned to them. Let's take a look at those centroids. So a couple of ways to do this. I like taking advantage of mate connectors. So we'll Control M there to add a mate connector. We can add it right onto this I-beam. You see that black and white center of, that is the centroid of that shape. So there's one. And we can add another one here to the T-beam, seeing that its center of mass is higher than I, and that definitely passes that gut check. And ours a little bit harder to get. We can hold down Shift, we can zoom in, but there's the R beam center of mass. And to find out what those values are, if you click on it, the origin is in the center of the part, so that's that value. we're really looking at the Z value. So surprisingly, the center of mass for R is right about in the center for a 6-inch tall beam. I is just a touch below center. And then the T center of mass is up a bit further there. Okay. We could also look at the moment of inertia. We're going to come back to this, right? And we see that the moment of inertia for the R, resistance to that vertical load bending, is 44. For the I, it's 22. And for the T, it's 34. So given these heights, we'd expect R to be the most resistant to deflection, but recall that that's almost twice the height of the I-beam and therefore almost twice the material cost. We found our centroids, and now we're into step 4. So step 4, we want to modify these beams to have the same cross-sectional area and therefore the same weight. So what we need to do is actually measure the cross-sectional area for each face. So if I click on the R, I have a cross-sectional area down here. I can copy it. We cannot yet use the measurement details to add a variable based on area, so we'll have to do that manually. So this will be area of the R beam. Okay, and this is going to be an any because it's not a length. Let's add it right in there. Inches squared. And this was manual entry, right? If geometry changes, then this needs to change. Let's go to the I-beam. Copy that value. And we'll add the inches squared. I really like how Onshape uses the units in their any type values. It can be really powerful. So we're going to not lose those just to make sure, it's kind of a check on our math. All right, so the area of the T-beam is inches squared. And this is also manual entry, just to help me understand that if I make a change, I would have to update these on my own. Okay. So similar to how we use the transform to scale it from the size we thought we wanted to the size we actually wanted, we're going to use the transform to scale it so that everything has the same cross-sectional area as the I-beam. So we're going to make the I-beam the datum, and everything else will scale relative to the I-beam. So we're going to make something called scale R. And scale R is going to be the area of the I-beam divided by the area of the area of the R-beam. However, when we transformed previously, right, we had an inch to inch ratio. Here, we have inch squared to inch squared ratio, and therefore we need to take the square root of this entire ratio. Okay. You'll have to trust me on this. It works out. We don't want to do the full scaling in both X and Z. So when we do the scaling of X times the scaling in Z, we get the right ratio. Okay, so we're going to set up another scale for T. This will be any, and we're going to do the square root of the area of I divided by the area of T. So this is our scaling ratio for the T. So We're going to modify the steps. This is step 4, so I'm going to pull step 6 and step 5 down here. Actually, let's just go in. Okay. So there's our scaling ratios and our areas. Again, those would have to be manual entry. Okay. And we can do our transform. So we'll transform the R beam by scaling it, not uniformly, but in X, we're going to pick scale R. In Z, we're going to pick scale R. And we're going to go around this corner down here as our point. And you'll see that our value got quite a bit smaller. So let's double check. The area of I is 6.067. The area of R now is 6.067. So another way I can confirm that it's doing what I want is when I look at my I-beam and I have 35.5 pounds, and I look at my R beam and it's the same mass. So that's our goal, is that when we're comparing these two beam strengths, that we're comparing the same amount of material to what's driving that strength and pulling it just into the shape. Let's do a transform on T. Scale T. Okay, and again, we can double check. I, 35.5 pounds, T, 35.5 pounds. Okay. So that's why things look a little weird, is that the scaling factor has brought them down so that they are all the same mass. Okay. To get these mate connectors to update, we can bring them down after that transform and we can compare their center of mass now. All right, step 5, we want to confirm the weights. We just did that. And we're going to measure the area moment of inertia for each beam. So we're going to measure a face instead of a part, and we'll click on the I-beam. And we find that the resistance to a vertical loading, right? The resistance to bending for this I-beam is 22.89. The resistance to bending due to a horizontal loading is much, much lower. But this is the piece of information that we are curious about. So I'm going to copy that. And we are going to add a new variable, MOI, for the I-beam. Let's go to any. So this is also manual entry. If anything changes, we would have to do our calculation and update this value. Repeat that. So you'll see here, this R value, the resistance to bending, is less than half the resistance to bending of the I-beam. And we'll see that when we look at the displacements. And last one. You'll see the T is in between the I and the R values. Okay. Step 6, move to the assembly for analysis. So we're expecting I to have a greater resistance to bending than T, and T has greater resistance to bending than R for the same amount of material. All right, in the assembly, I've brought in all 4 of the parts. I have fixed the support, so it is not going anywhere. And I have set up revolute mates between the support and the ends of the beams. And this is kind of mimicking a simply supported beam with a pin at one end. When we're doing analysis or simulations, we have to have material assigned to all of the parts. And you can see that they all have aluminum assigned. Okay. So we have the first part fixed. We've got some basic constraints set up. They all have material. It's time to add the forces. So I'm going to add the force to the R-beam. We're going to do 300 pounds. And the load direction is going to be on this top surface of the R-beam. Okay. I see it's pointing up. I want to flip it. So I have 300 pounds going downward. We're going to rename this to the force on R. I'm going to add another force onto the top of the I-beam. Again, 300 pounds. The load direction is on this top surface, and we'll flip that and name it. And last, we'll apply a force onto the top of the T-beam. And let's rename that one. Okay. So now we need to set up our simulations. Simulation 1 will show all 3 of them. So that'll be the fastest way to get done. And let's just go ahead and show results. Okay. We could create multiple simulations. I can go ahead and start this. Actually, this might not work. Let's switch this to bond all touching faces. Try that again. I can add another simulation. Okay. In simulation 2, I could have just the R force, right? I can get rid of I and T. I could add another simulation. Oh, yeah, well, we're going to let this keep working. So we're only 20% done. So in my second simulation, I'm going to do just the I-beam. So we'll leave that one selected. And we can add another simulation. It'll be just the T-beam. So as of right now, we can't rename the simulations, which I would like to be able to do, but we're going to almost be done here with the simulation 1, which is all 3 loads. All right, so right now we're looking at stresses. I want to switch over to displacement. Okay. And we can see that, move this over. There. With this deformation scale of 3,000, that's a little much. Let me go 1,000. And where that shows up is here when we say show deformation. Even that's a little on the high side. All right, and we are almost there. So here we've got our max displacement is 2.8, and that is showing up on this R-beam. I can see at the top of my R-beam, I've got that 2.5 thousandths, 2.6 thousandths. On the top of the I-beam, I've got 1.3 thousandths. Over here on the top of the T-beam, I've got 1.6 thousandths of an inch. So you can see that given these loadings, that the I-beam is the stronger beam for supporting against a vertical load. So I hope you've enjoyed this demonstration on how to apply some scaling, some development, some analysis, and some simulation for looking into different beam shapes. Feel free to try this with your initials, your school initials, and see what results you get. Thanks.